Okay. If you remember, like this scheme, we talked about visualization, inspection of the data, how are they after that you analyze them, you recognize that maybe you need to clean some parts. We heard about data cleaning and data imputation, missing data, and so on. After that, you have your data prepared. You need, most of the time, you need to do some data transformation. This data transformation, it really depends on the type of your data and the type of machine learning method that you are going to use. So the reason that I'm here brief, because this is what I'm going to tell you. It's very general about whatever, let's say, machine learning approach is more or less correct. But like my colleagues that already talk about deep learning, supervised, unsupervised, they will show you specifically on those cases what do they need. And after that, you do this data transformation. You are ready to feed your data to your machine learning approach, and then you would have your machine learning model. In my opinion, this plot misses like another arrow here, because of course, after that, you evaluate your model and you see that it's not exactly the result that you wanted. Many times you need to go through this cycle again and do the data cleaning or data transformation. To me, happened a lot that I needed to do another type of data transformation to get a better result. So keep in mind. And believe me, like training the data is not the hard part. The hard part is the pre-processing. So really keep it close to your heart. Okay, so transforming input data is often crucial and sometimes even mandatory, because it can improve model performance. Sometimes if you don't do the transformation, like for example, scaling or normalizing the data, your model doesn't learn at all. I mean, it really happens many times. This transformation is mandatory because it needs to meet the statistical assumptions. So some methods, they require variable normality and linearity. And they can also speed up the model convergence, of course, because understanding of the model depends on these transformations. So if the model can understand better, of course, it can converge faster. Balancing the feature selections and the features of the model, it really influences your model, and then it can reduce the skewness and outlier what we would desire. Okay, so very let's say regular ones on the data transformation are linear transforms. These methods, min-max normalization, that are all of these methods that I'm talking about here, they are already implemented in scikit-learn. And if you don't like Python, I believe also in R and other languages are implemented as well, since they are widely used. So in this model, you rescale the data from original range to a new range, as you know that for your model is needed. Many times it's like a 0 and 1, but based on the physics of data that you know, maybe you need to do it from like 2 to 100. I mean, it depends on you and your knowledge, let's say. And so here in this example, you can see that using scikit-learn, you import it, and then you have your data, and you just do this magic word of fit transform. Now you are going to see it in the hands-on session a lot, because with whatever method that you import, basically then you do the fit transform, and your data would be in, let's say, that scale. So you normalize the data back and forth here. You save the transform data to the file, and then you can again load the transform data to do the rest of your analysis. Another method would be a standardization, that you rescale the data distribution to zero mean and unit standard deviation. Here you see the method, it's called standard scaler again, and you do the same. So you do the fit transform, and sorry. And you save it basically. Here, important point to consider is that this transform make much more sense for normal distributed variables. And consider that mean and standard deviations are sensitive to outliers. And in that case, consider to use the robust scaler. And this transform produce negative values, so maybe you need to filter them by certain activation functions. Okay, another linear transformation that we have are the ones that they scale to unit norm. So L1 norm and L2 norm, that the mathematical definition you can see here. So from pre-processing package of scikit-learn, you import the normalizer, and you define which norm you would like to transform your data. You fit your data, and you save the file. Here you can see that you can use these joblib or pickle. The joblib basically should be performing better, and it's more optimized for scikit-learn. So these are just, let's say, some tricks here and there. Depends on your data. Sometimes you need non-linear transformation. Of course, if your data are power law and so on, it doesn't make sense to transform them in a certain way. Instead, they may require or perform better with the Gaussian distribution variables. These are all depending on the knowledge that you have from the data. So power transform, they aim to make the probability distribution of a variable more Gaussian and less skewed. So you can here see some example of this kind of let's say distribution, and with some transformation that Box-Cox and Yeo-Johnson that you can see here. You see that after applying to these methods, they get a lot closer to Gaussian distribution. The only difference is that Yeo-Johnson is extension is more complete than Box-Cox, because that one is only applies on a positive data, while Yeo-Johnson it's both for the positive and the negative one. And another example here, you can see that something useful maybe you could use for your data is a scikit-learn pipeline. With the scikit-learn pipeline, you can apply different type of transformation on your data. For example, here you can see that I get the minmax scalar, and then I apply the power transform as well. So here you can see that there are two steps. So with the pipeline, you can create different steps as you wish on your data. Another method would be these quantile transforms that aim to make the probability distribution of variable more Gaussian and uniform. So given a random variable, the quantile function maps its input to a threshold value x. So the probability of x being less or equal than x and p based on the function. Here, the same example as before, and you see that after the quantile transformation, how they are changing. Here, very small. You cannot probably see very well, but I explained to you that here you can use scikit-learn quantile transformer method. You again with the pandas, and then you applied scikit-learn to your data. Here you can see that in some cases, maybe also this transformation can destroy your data. For example, you see that if you have Gaussian, uniform, or bimodal, after the quantile transform, you get like a normal Gaussian, that maybe this is not your desire. I mean, you should always check after a transformation that maybe you would, on one thing, you didn't add a feature to your data that's not the case, let's say. So another type of transform is transforming categorical data, that, for example, your data are consist of keywords or categories that they are not values, but you need to encode them to the numerical values. Common encoding in this case are ordinal encoding on and one-hot encoding. For example, here you can see that if I have some categories like star galaxies and quasars, I can put them in value in this case. And here you can see the example of the this ordinal encoder and one hot encoder, and another one that here is you can see in this way, always in the scikit-learn pre-processing library, you can add to your system, and you always do this magic fit transform. Okay,